Welcome back to another video. This time it's going to be about boats and lakes and how far a boat travels after it shuts down its engines. Um, in this problem we are going to use calculus, and it's going to be um, simple introduction to differential equations and calculus and integration, and how all of these things, come up in physics. And this, I think, is a very good example of how we use, or physicists, or of how calculus appears in physics problems. So we have a boat here and a lake, and the friction that the water of the lake exerts on this boat, if the boat has a certain velocity. So we can also express this like the force of friction equals minus some coefficient times, and this is a constant coefficient, times the velocity. So if the velocity is very big, then the force that is decelerating the boat will also be very big. This is proportional, a linear um, like correlation here. Okay, we have initial velocity in this particular example that is let's say 0 seconds. At the time 0 seconds, um, it will be 4 meters per second, and after 3 seconds it will have a velocity of 2 meters per second. So we can say that, if this thing is here is correct, then after 3 seconds the velocity will be half the velocity that it had before. Okay, and well, let's start. We have a force that is going to the negative direction. We have a kind of friction coefficient here, which is constant, and we have a velocity. Okay, so the force, if we want to, use calculus and use differentials, then it all it almost always will be handy to write the force like m times a, and m times a is obviously going to be m times dv over dt, so a change in velocity over time. That equals minus k times v. Okay, and now what do we actually want to achieve here? Well, we want to calculate the damping coefficient, right? Or we at least want to calculate the velocity. That we want to find an equation for the velocity. So, well, what we have here is a differential equation, first order linear differential equation. Because this is actually just v dot equals minus k over m, and this is a constant, times v. So we have the function in here, and we have the derivative of the function, and that is a very simple case of a differential equation. And how do we solve that? Well, we just multiply by dt on both sides, and bring all variables, or separate the variables basically. So this method of solving the differential equation is called separation of variables. So and it involves just bringing the variables of what we want to have on one side and everything on the other side. So we want to have the velocity, so we have the differential here, dv, and we also want this v to be on the other side, so let's just divide by that. So dv over v. Okay, and when we have that, we can integrate over it. So we say the integral over time here over velocity, from v0 to v, and let's just call this v prime to be mathematically less gross here, and the the time is going to be from 0 to t, and let's call this t prime. And we can actually just rename those things, just so these limits of the integral have not the same name as the variable we are integrating over. Okay, let's calculate this. That is the natural logarithm of v, or actually, yeah, v minus the natural logarithm of v0 on the one side, and on the other side, this is constant, so we can just leave it in front of the integral, minus k over m times, this is just going to be t, right? Okay, then we just write t, and on the right side, that is going to be natural logarithm of v over v0, and that equals minus k over m times t. And if we just apply the exponential function on both sides, so that's the inverse basically of the logarithm of the natural logarithm, we say like this, then those two things cancel out. So we can just say, okay, those two things cancel out, and we are left with v over v0. V over v0 equals minus k over m times t, or actually e to the power of minus k over m times t. Okay, and this minus k over m here, we can also call this like mu here. We just redefine this as number as mu, so I don't have to always write it. Okay. And if you want v to be alone on one side, just multiply by v0, and we are left with times v0 here. E to the power of minus mu times t times v0. Okay, how do we how do we continue solving this problem? Well, what do we want to know? We want to know the distance that it has traveled in that time. So we want to usually say v equals dx over dt, and solve for dx and then integrate over dx, so we get the whole distance, the whole distance that the boat has traveled. So we just say v equals dx over dt, and that equals e to the power of minus mu times t times v0. Okay, and we multiply by dt. So we have dx equals e to the minus mu times t times v0 times dt, and we integrate over that. Integral from 0 to s, let's say. So s is going to be the distance that it has traveled, and on this side we're going to integrate from 0 to t, and let's call those things just t prime, as we did above. That's just to be mathematically more correct, or less gross. Okay, so we can say that s equals, this is constant, so just leave it in front of the integral, and that is going to be minus e to the minus mu times t over mu, from 0 to infinity this time. Oh, not to t to infinity, sorry. I am very sorry here. Okay, because we want to, let this boat travel an infinite amount of time, and then at the end it's going to be, or actually, if it's a perfect fluid and if it follows this rule here perfectly, it's never going to stop moving at a certain velocity. So that is why the limit here we effectively take the limit here, and that is very handy in our case. Um, so we actually can calculate how far it will be going, how far of a distance it will travel um, at an infinite time, at an infinite amount of time, within an infinite amount of time. I'm sorry, I'm not a native speaker, so uh, hopefully you let that slide. Okay, and that's going to equal, well, we just plug in infinity here, and e to the minus mu times infinity is e to the minus infinity, and that is going to be 0. And if this is 0, then the whole expression here becomes 0. So we've got v0 times 0, and then minus, well, what have we got when we plug in 0? E to the minus 0, oh, that is t prime, I'm sorry. E to the minus 0 is going to be 1. And then we have just v0 over mu times 1 over times minus 1 over mu. And then we just have this is equal to v0 over mu. Okay. Well, this is the distance that it will be going. So now the only thing we need to know is this mu, so that basically damping coefficient divided by the mass. Okay, and how do we get that? Well, we have our initial conditions here, right? These are our initial conditions. And so we can just say the velocity, we have the equation for the velocity. So we say v of, or v0, let's say v0, so v of 0 seconds. Oh, actually, let's do it. Okay, we had the initial condition that the velocity after 3 seconds is 1/2 the velocity before those 3 seconds, so times the initial velocity that it had before those 3 seconds passed. So if you just plug in 3 seconds for t in this equation here, so let's say v of 3 seconds, this is equal to 1/2 v0, right? v0 over 2. That is equal to e to the minus k over m, and we want to calculate mu, so minus mu times t, and t in this case is 3 seconds times 3 seconds times the initial velocity. Okay, then we have we need to solve this for mu, and after some algebra, some basic, and if we apply this the inverse function of the exponential function, so the natural logarithm to it, I think we will get something like the logarithm of 1 over 2 over 3 seconds. Let me check that. Okay, I just checked that, and it's correct, and that equals basically minus mu, and if you put a minus sign in front of here, then we get mu, and that is a value like I think it's around 0.23, and then we can just plug this in here for mu, and we get the if we have the initial velocity and we have this not damping coefficient, this friction coefficient here, then we can calculate what we will get. So let's say if v0 was 4 seconds, then it's 4 seconds, and mu was 0.23, oh, I'm sorry, meters per second, and this was 0.23 seconds. Then we would get, well, this time second is meters, so the dimensions are correct, and I think it's going to be 4 divided by 0.23. Yes, I've got it here. It's around 17.4 meters. So yeah, there we go. We have just calculated how far this boat will be going if we have infinite time. Okay, I hope you understood the basics of this differential equations and calculus. I think it's a very good problem to, um, show show to you how physics and calculus are basically very tight together, they're merged, like, you know. Okay, thank you for watching. I hope you enjoyed the video, and point out any mistakes if I've made some. And we will see us in the next video, I guess.